P and take then the dual function, but your integration is on this surface now. What is here? It turned out that it is exactly the same formally adjoint operator. It is written absolutely the same way. But here, you should have the tangential derivatives. Tangential derivatives. And what is, for example, the dual operator for divergence on the surface, defined by the Günter's derivative? Divergence, dual to the divergence is simply gradient on the surface. And the dual to the gradient is divergence. So they are reciprocally, so mutually the adjoint operator, with minus, with sign minus, it's here. So adjoint to divergence is gradient, adjoint to the gradient is divergence with minus. And since the Laplace-Beltrami operator is divergence multiplied by gradient, so the Laplace-Beltrami operator is then self-adjoint. Because if you take dual, so you should put star here, and interchange. And we'll get the same Laplace-Beltrami is self-adjoint operator. It's easily seen this in this definition. Yes, it's written here now. And it is interesting also to find what is dual operators to our basic operators. Dual operators to Stoke's derivatives are same, the Stoke's derivative, but we've changed the index. So to gk is minus gk or kg. This is most interesting from my point of view. The dual operator, adjoint operator to Günter's derivative is minus the same Günter's derivative, but plus something. Function multiplied by function, well, this is the test function. So this addition here, it's very interesting function. It's a normal component, of course, due to this, but this function is simply gives you the mean curvature of the surface. So the dual operator to the Günter's derivative is the Günter's derivative is minus function multiplied by mean curvature of the surface. Here, when we are on the usual well in Rn, this disappears because the mean curvature of the flat surface is 0. Mean curvature is 0. So this disappears and you have the same formula that the dual to dg is minus dg, which is in Euclidean space. But as soon as you are on the surface, you have such a picture that the dual to the Günter's derivative is minus Günter's derivative, but minus also the curvature, which is quite natural. Yes, here is written. So you have to define to divide it by the dimension also. Dimension, then it is exactly the mean curvature, Gauss curvature. Yes. Here are some properties of these differential operators. Properties are here is the linear dependence described, and many properties they have. We use it very often in our work. There are many properties. But now I want to speak a little bit about boundary value properties. That's why I speak these properties, because I have only last 5 minutes, I think. Maybe we'll start with 5 minutes later. Okay. Boundary value problems. What we have now, open surface, the part of the surface. If you erase one part of the surface, you will get the open surface. Yes. This is now boundary. Gamma, and you have surface, it's all here. You have some C surface, and this is the boundary of the surface. Now we have this situation. And we have partial differential equations on the surface here, open surface, and we would have some
boundary conditions on this boundary gamma. And this will be the boundary value problem. Usually you have, in this space, in Euclidean space, you have domain, omega, and you have differential equation here, and boundary conditions on this surface. Boundary conditions. That means, for example, that the trace of the function U plus is equal. This is the so-called Dirichlet condition. You take traces on the surface and you prescribe their values there. And inside you satisfy certain differential equations. That's the differential equations which you have on this Euclidean space. What are differential equations here on this surface? You have some differential equations with tangential differential operators. For example, Laplace-Beltrami operator. And you have some boundary conditions. Here you are. You have Laplace-Beltrami operator on this surface, on this open surface, and here you have Dirichlet condition on the gamma, on the boundary. Or you have normal derivative, but the normal derivative with respect to this boundary. This derivative is normal with respect to this surface, means that here it is. It is tangential to the surface, but normal to the boundary. Tangential to the, because normal to the boundary are a lot of vectors, but such vector which is tangential to the surface and normal to the boundary, it is only one vector field. So you have, this is the Dirichlet boundary value problem, this is Neumann boundary value problem. We can consider also, here is definition of this normal derivative. We can consider also, we considered now, we are now finishing this work, partly finished. We consider also this mixed problem. When you divide the boundary in two parts, one part you have Dirichlet condition, another part you have Neumann condition. And you consider such, why we need to consider such boundary value problems? These equations describe the heat conduction on this surface. Heat conduction. You have some sources of heat on the surface, and you have some initial distribution of heat on the surface. You know temperature at any point of the surface, and you look